Thank you for having the patience this afternoon. I'd like to thank you for joining us for a seminar on contract 14308, ozone in the lower atmosphere and its contribution to high ozone concentrations at ground level in the Southern San Joaquin Valley. Additional information about this project is available from our research seminars webpage. For those of you online, questions for the speaker can be sent to the website sierra@calepa.ca.gov. We also need to go over a couple other housekeeping items. The exits in the case of the event of a fire alarm. These are located at the front of the room on either side, and we are required to evacuate immediately, and please don't use an elevator. Exit down the stairway and gather at a relocation site across the street. Oh, this is good. First, I'd like to give a general overview. The unique topographical and meteorological conditions in the San Joaquin Valley present a challenge to regulatory efforts to comply with ozone standards. This plot shows a map of the San Joaquin Valley with Stockton at the north, Fresno in the middle, and the southern part of the valley with Bakersfield. And we'll be talking a lot about that area in this presentation. The San Joaquin Valley is an intermountain valley, approximately 250 miles long and averaging 80 miles wide. It's bounded on the east, west, and south by mountain ranges. And air flows into the valley from the San Joaquin River Delta, and topographic features restrict the air movement both into the valley and out of the valley. In addition to the restrictions of the airflow, the high pressure events that often occur during the summer months limit the vertical transport of pollutants vertically, and this allows pollutants to accumulate over time. This plot shows trends in the San Joaquin Valley of the 8-hour ozone standard. This is 75 parts per billion. The new one is 70 parts per billion. And this shows the trend from 1990 to 2015. Ozone is formed in the atmosphere through photochemical reactions between oxides of nitrogen and volatile organic compounds. Dominant sources of these precursors are VOCs and NOx emitted by gasoline and diesel vehicles, cooking, biomass burning, and regional biogenic emissions. Transport of pollutants within the San Joaquin Valley plays a dominant role in the violations of the federal ozone standards, and these are still looking to be met. Regulatory efforts to comply with the ozone standards will require improvements in our knowledge of these factors controlling the ozone formation, transport especially, horizontally and vertically, and precursor sources. Today, Dr. Faluna will talk about some of the work he has done to answer the general question of ground level ozone in the San Joaquin Valley and how it's influenced by residual layer storage, daytime entrainment dilution rates, and nocturnal mixing. Dr. Faluna is an associate professor at the University of California, Davis in the Department of Land, Air, and Water Resources, and he received his PhD in meteorology from Pennsylvania State University. After working as a consultant and then a postdoc at the Advanced Study Program at the National Center for Atmospheric Research, he joined the Atmospheric Science faculty at UC Davis. Professor Faluna's research interests include airborne investigation of vertical mixing and near-field pollutant dispersion, observational emission estimates, and meteorology of coastal fog, planetary boundary layer dynamics, biogeochemical cycling, and atmosphere-ocean photochemistry. Please join me in welcoming Dr. Ian Faluna.
Hey, thank you, William. Thank you, everyone, for coming to hear me speak today. I wanted to, there's a lot to cover. Is this, yeah. Great, yeah, thank you. Okay, so I'm going to cover the work we did under ARB contract, collecting data in the San Joaquin Valley. And the project was really focused on, this is a picture from the cockpit of the airplane to show you the valley as it looks like from aloft. And we're going to discuss how the vertical stratification of the atmosphere and the mixing thereof affects the ozone levels at the surface. And this is a study that we collected something like 160 flight hours, where we went down on 5 separate occasions and tried to follow the air mass, track the air mass and measure it for consecutive days in a row throughout the diurnal cycle. So it's a pretty unique data set in my opinion. We measured ozone, NOx, and methane, as well as meteorology. And then it started in 2015, but because of contracting delays, we only did 1 deployment in 2015. We wound up doing the 4 other deployments in 2016, which happened to coincide with the CABOTS project, which was there, which involved a NOAA ozone LiDAR and San Jose State launching ozone sondes daily at the coast. So we were an integral part of that as well. So in support of that, we also received additional funding to do another 42 plus hours focusing on that air mass more specifically in the daytime to study the ozone budget. So I'm just going to include some of that as well, I just wanted to delineate that clearly, that there are flights that we call EPA flights, which are those in conjunction with CABOTS, and then also these residual layer ozone flights, which are from this contract. This is kind of a dense outline, but I just wanted to let you know there's 4 basic thrusts that are coming out of this work. The first one's already come out, and that was a paper by Almaraz et al. That came out in February and created sort of a traditional fertilizer storm, if you will. And it suggested that our measurements of higher NOx emissions in the San Joaquin Valley were consistent with the modeled emissions from colleague Ben Holton at UC Davis. So I'm not gonna, well, I'll go over this a little bit. The next work on here, number 2, we're gonna talk about the ozone budgets and the actual photochemical reaction rates, production rates we have, measured and discussed some of those, methane emissions and NOx emissions, and I'll go over briefly how we determine those and how they turn out to be higher than expected. Then we're gonna look at the dynamics, so we'll actually look at the turbulent dynamics of the boundary layer in the valley and how this mixing of entrainment influences ozone. And then the last thing is nighttime mixing, and I put this last because we have this version, Caputi et al., which is currently in ACP discussions. So if you wanted to dig into the details and comment on it online, you can do that. So the link is here. But what we're interested in there is the other side of the diurnal cycle of ozone and how does mixing at night affect the following day's ozone. So I hope to get to all of those, although we're a little behind, and I might have to trim out some of that at the end. So William already gave us a sort of overview of the problem. The guiding motivation for this project was that we were going to figure out to what extent do the ozone challenges at this bottom of this valley affect the residual layer, how much do they depend on the residual layer storage of regional production of ozone? How does that vertical mixing in the daytime of entrainment into the boundary layer affect it, and how does nocturnal mixing affect it? So some of the questions, well, we can talk about this. As I mentioned, this Almaraz et al. Paper suggested that there may be larger agricultural emissions of soil NOx that may come from agriculture in the region. And then David Parrish recently published an analysis of air basins throughout the region, indicating that there was improvement that was much slower in certain regions of California that are consistent with this hypothesis of the soil source. And then basically, I want to talk about the, again, the entrainment. How important is that mixing in the daytime at the top of the boundary layer? How does recirculation affect the ozone levels and the nocturnal mixing? So this is a kind of a zoom in of the parish. Parish analysis did it through air basins across the region. This is violations of the 8-hour ozone standard. This is broken down now by county within the San Joaquin Valley Air Basin. And so you can see these top 3 counties. This is Los Angeles in dark as sort of a reference. And you can see that the Tulare, which has Visalia in it, and Kern, which has Bakersfield, the large urban areas, have a similar sort of decay across the last 10 years in violations, or decrease in violations. But these other more agricultural remote counties don't seem to have that same sort of trend. So this is an intriguing aspect of the problem there. If you look closely, and this is in the ARB Almanac as well, that there tends to be more and more violations as you go deeper into the valley to the south. So this is a 10-year climatology that we run for Fresno, Visalia, Bakersfield, Arvin. That's a progression southward into the valley. And there's a couple of interesting points I like to make here is that aside from Arvin, the other 3 sites tend to have this trimodal violation seasons. So we use this as kind of a crude estimate of forecasting when we might be down there chasing these ozone episodes. So you can see that there's a peak in mid-May, there's a peak in sort of mid to late June, and there does seem to be a lull in mid-August. And then mid-September, you have another peak, and then it decreases as you'd expect. But down at Arvin, which is really at the bottom of this basin, or downwind end, I should say, that you see that it's sort of just a gradual buildup over the whole ozone season. Okay, so this is the conceptual model that we're applying in the aircraft studies. And this is sort of the classic, cartoon, comic book picture of what a boundary layer does throughout the day. And that is, it's growing in the daytime. From the morning, when you start heating the surface, you could create this convective boundary layer. Sometimes you'll get this fair weather cumulus, which we don't see a whole lot of in the summertime in the San Joaquin Valley. And then at night, once that surface starts to cool, you generate this stable boundary layer, which due to some sort of shear mixing, does communicate with the surface, but it's restricted to a much more thin layer that we call the nocturnal boundary layer, or NBL. And then there's this layer aloft, which has basically the aftermath of the day's photochemical production of the boundary layer, in the mixed layer here being what we call the residual layer. And the important thing here is that the residual layer is decoupled from the surface. And so chemistry happens there without the presence of the surface. So we'll talk about that. So we have these flights. These black bars indicate the flights throughout the diurnal cycle that we did. They were typically a little over 2 hours. So we go for these flights. We brought down 2 pilots, 2 flight scientists, crews, so that we could do these, cycle them throughout the diurnal cycle for usually 3 days consecutively. And so what we were able to do then is look at, for example, the difference between our flights at midnight and our flights in the morning, and infer something about the mixing and chemistry that occurs overnight. So that's one of the topics. And then we flew these in the middle of the day as well, and then sunset flights. And this blue, or this greenish box, really showing up. Okay, the cursor's not showing up online, so I'm just gonna have to indicate verbally that greenish box is where those EPA flights were, which were really focused on the daytime photochemical production. Now, this is the classic cartoon of the boundary layer, and we'll talk about these terms in just a second a little bit more. The chemistry, or the simple mixed layer model that we apply to the chemistry and our observations. But really, it started to bother me that this picture isn't exactly, it's not really that, it's misleading in some ways. So what I did was I put up a simple model of the mixed layer that we use in my sort of graduate class. I have the students code this up so they can look at how the boundary layer changes. And I just scaled that to the cartoon's initial boundary layer size, which is like the morning when the sun first starts warming the surface, to the ending. And that's what this blue line is. So what you notice is there's actually growth throughout the day. It's not all just focused in that early morning period. There's gradual growth. And so this gradual growth is where there's this important mixing occurring afternoon that we focus on, this entrainment mixing from above. Now, this green line is the same model where you apply a consistent vertical velocity, a subsidence that you usually have in fair weather conditions, which is constantly pushing down because of low-level divergence. It's pushing down on the top of this lid and suppressing it. And if I put in a vertical velocity like we expect that exists in the San Joaquin Valley, you see that the boundary layer depths are significantly altered from that. So this subsidence is an important aspect to these boundary layer dynamics. But I wanted to just make that point, and I'm going to try to modify this cartoon so that it's more realistic, because overnight usually these layers tend to sink as well under this subsidence, fair weather subsidence. So you don't have this flat top for most of the day, as the cartoon indicates. Okay, so this is a zoom in of the valley, and this is actually, there's this Sabrones fire over here, northeast of Big Sur. And we have a monitoring station, Choose Ridge Observatory, that was active during CABOTS, and that data set is available publicly. And then the green lines show you the flights that I'm calling the EPA flights, where we focused in the afternoon. They were longer flights. They tended to be 4 hours, and we really focused on the chemistry and the boundary layer during the daytime. And the blue lines indicate the flights that we're calling these residual layer ozone flights, which were really concentrated between Fresno and Bakersfield, the entire extent of the San Joaquin Valley, but really oriented along the 99 corridor, because these yellow dots that you'll see are airports in which we flew almost to the ground, so we were able to make deep vertical profiles to just about the surface throughout the night and day. And then these white stations are ARB network stations that we use in some of our surface analysis. This is what the general plan of the flight strategy was, where we would do these 2.25 hour flights. We'd leave Fresno, we'd do a deep profile. Well, deep in this case, we tended to focus in the lowest 1.5 kilometers, sometimes up to 2, sometimes up to 3 if we had extra time. Do a deep profile around Fresno, and then we would do these transits across down the valley axis and do, again, touch and goes at these airports along the way. Sometimes we did profiling that way. Sometimes we did level legs and then the profiling as indicated here. So we tried to probe this lower layer of the atmosphere quite thoroughly. This is what a time series would look like. The blue is ozone, the yellow down below is NOx, and then the black lines are the altitude. So you can see this top one is a midnight flight, and you can see that when we go down low, when we do the profiles down, you can see the ozone drops. You can see these strong vertical ozone gradients, and the NOx goes up. So the opposite directed NOx gradients at night. And then this is a following afternoon flight where you see a little bit of the opposite. You see as you go up higher, the ozone is lower, and the boundary layer then has higher ozone in general. So this is what the time series typically looks like. This is the standard kind of figure you would see for an airborne experiment, but I'm gonna, because we have so much data of this, I'm gonna average a lot of these and just look at mean profiles in a lot of cases. Okay, so the general meteorology situation is that if you look down low somewhere in the boundary layer, like 950 millibars, you see that's the standard summertime flow is this northwesterly flow offshore. You can see it kind of coming in, the break in the coast range, and then invading the valley and flowing in a similar direction, but this direction here is really forced by that valley mountain circulation from the thermal forcing of that heating of the mountain and the valley, driving this up valley flow. But it is aligned with the standard meteorology offshore. And if you go up a little bit higher, to say like 3 kilometers, which is about, this is actually 2.5 kilometers, 750 hectopascal heights, which is below really the main peaks of the Southern Sierras, you see that the flow is generally, there's this kind of climatological trough, and you have generally, geostrophically, you have these southwesterly flow aloft. And that's what we see at Choose Ridge, which is at 1.5 kilometers. And so this flow is coming into the Sierras, but notice that this is North American regional reanalysis data. Notice that the flow kind of stagnates here at this altitude and eventually kind of gets pushed around to the south and to the north around the bulk of the southern Sierra Massif. So this is a really important region that we're focusing on, this sort of stagnating air mass aloft in the San Joaquin Valley. This is a cross-section that I really like to look at. This is terrain data from offshore of Big Sur. This is where Choose Ridge is in the Coast Range. This is Salinas Valley. Then the other range here, and then this is the San Joaquin Valley, and then gradually up to the Sierras. So this is an actual physical cross-section, of course with exaggerated vertical coordinate, but then this is our average profile of ozone, this blue line, so you can see this sort of high ozone down low. This is daytime. And then you have this sort of intermediate region here, which is somewhere between the high ozone of the boundary layer and this intermediate region here, which I'm going to be calling a buffer layer. It's a layer that's not technically a boundary layer, that's in constant communication with the surface, but it's definitely being influenced by the surface. And then aloft, we have the kind of the traditional free troposphere here. Now, this is a photograph from winds measured by the Visalia sounder, the radioacoustic sounding system. And these just show you that you have typically in the daytime, this is over the 2 months of the project, you have this northwesterly flow. So this is a photograph, so you're looking at where the wind is coming from and point is going to in the arrow. And then this gives you a wind speed average, and this gives you the vector average. So what you see is up here, the wind speeds still may be something like 5 meters per second, but they're back and forth. They're sort of, they're alternating in direction so that their vector average turns out to be almost the null vector. So this is that stagnating layer that we're intrigued about. This is SONS from the CABOTS, from the San Jose State CABOTS ozone sonde data set, which just looks at the wind, so not ozones, but just looking at the winds offshore, and you have what I was explaining earlier, you have the northwesterly flow, and then once you get aloft a little bit, you have this southwesterly flow. So this is what the flow looks like before it's disturbed by the terrain. So this is what I'm calling this 3-layer system. So it's not a traditional, like a, Kansas kind of boundary layer where you have a boundary layer that's distinct, and then you have the free troposphere above, and those two are communicating. Here we have, I'll put in here the average profiles to scale. Here we have a well-mixed boundary layer that's kept pretty shallow as far as these kind of solar inputs we get in the summertime in the San Joaquin Valley. The average boundary layer is something like 600 to 700 meters. It's a little bit deeper to the south, but it's relatively quite shallow. And I would argue the reason for that is because of the mountain system that induces subsidence, which is pushing down and resisting the growth of the boundary layer as it would be free to grow in a place that didn't have this strong mesoscale subsidence. So this layer really becomes the important one. Well, I mean, they're all important, but this is a layer then that you really want to focus on, and this project has the observations to really dig into, and that is this layer that's it's part polluted boundary layer as this stuff gets lofted up the sidewalls of the valley. This happens on a sort of more of a diurnal scale as opposed to convective boundary layers, sort of 15, 20-minute scale. Air is getting lofted up this side here, lofted up this side, and it just sort of sits in this region then where it stagnates. It's mixed with air from offshore, so baseline air, cleaner air, but it sort of stagnates there and has this partial mixed character mixed between the boundary layer and the free troposphere, so I call this the buffer layer. Okay, so I want to just show you an example of this because this is a beautiful example from the CABOTS data set that AJAX, the AJAX NASA project sampled. This is a picture of the Alpha jet, the jet that NASA operates to make measurements throughout the whole western U.S., and a picture of the scientific aviation Mooney. This, of course, is a picture that Steve Conley gave me, and he loves, of course, probably because the Alpha jet's below the Mooney. Sure, he staged that. But this is near Livermore or something. But these are profiles then that the AJAX plane did. So these are instant, well, more or less, a couple-minute profiles they did. In the dark blue line is at Bodega Bay. So this is what the profile looks like, say, of CO2 offshore. And then they did one over Visalia, where the NOAA LiDAR was, and where we were also working, in the light blue, the cyan. And we can ignore the other stuff for now. But the point is, if you look at CO2, there's this intermediate region in this buffer, what I'm calling this buffer layer, where the CO2 is depleted from all the agriculture and fixation that's happening in the valley, but it's getting lofted. Here you see methane, similar things. You see these little sort of like discrete layers of methane that have been lofted up there. Who knows how long ago, 1-2 days ago or something. And then you see ozone, kind of we've already talked about. And then you see water vapor, a similar type thing. You see in the valley, in Visalia, you have this elevated water, but it's not as high, of course, as the boundary layer would be. And the thing I love about this is formaldehyde, which we know has a very short lifetime, something like half a day. You see this is the boundary layer in Visalia of formaldehyde production, and then you also see this intermediate layer. It so discreetly comes up in this profile that this, on 12-hour, 24-hour timescales, air is getting lofted into this intermediate buffer layer here, and then above it's close to background. So this is the 3-layer system that I'm going to keep talking about. This is a film that Andy Langsford from NOAA took in Visalia of one of the times when that plane was doing those missed approaches. Almost touchdown, so you see that we take data all the way down to a couple meters height. And we do that at all the airports, Fresno, Delano, Bakersfield, and Visalia in this case. Okay, so I want to explain briefly how we do the actual analysis of our data set. And the first thing we do is, again, we track this inversion height, which is all the important, this mixed layer height. We do that in the afternoon, and we measure its growth rate, and that's a measurement we make here. And what we do then is we also measure its gradients in the horizontal. We look at how it's horizontally being advected. Typically up the valley, it's lower towards Stockton, higher at Bakersfield, so there's an advection of the boundary layer height in that direction up valley. Then if we know what the average vertical velocity is, which I argued was important, then we can use all of these terms and estimate what that entrainment rate is. That is, what is this growth rate? How fast is air in the mixed layer incorporating air from above into it? This is a key component. Then we look at, so we do that for the budget of the height, then we do that for any scalar we want, CO2, methane, water vapor, potential temperature, and ozone, and NOx, and methane, and anything else we measure. These represent the readily observables from our flights. We spend about 3 or 4 hours in the boundary layer and profiling throughout the day to capture these average values. And we put all this in, and we're able to then solve for certain things in the chemical budgets. For example, we can solve for the surface emissions for something that's not chemically active, or we can, if we estimate what the surface for ozone, for example, what the dry deposition rate is with the deposition velocity, we can solve for what the net chemical production is. So that's the basis of our methodology. I'm going to skip that for time's sake, just to show you that how important is entrainment. It's important, but to varying degrees for different scalars. So this is what the entrainment rate results look like for the 6 flights of the EPA days, which happened in late July and early August. Again, in support of the CABOTS project, which had the ozone LiDAR from NOAA at Visalia, and we were in the air mass that was upwind of Visalia in the afternoons. And so I'll just point you to the averages here, just to show you that, well, we have to use the WRF model to get the subsidence rate. So that's the one missing observable that we have to rely on a model to do. So we've gotten lucky. We're working with an eager, hungry, superb new faculty member, Holly Oldroyd at UC Davis in civil engineering, and her quite capable graduate student, Aaron, and they're running this WRF for us, and they're doing it with different PBL schemes, so we can kind of start to investigate what's controlling the modeling dynamics. But we rely on that subsidence rate, And then we can solve for these rest of these things, so we get an entrainment rate. And then we also can do that, like I said, for potential temperature, and through that, we can estimate what the actual sensible heat fluxes are from the surface, which is really what's driving a lot of the boundary layer dynamics. So in doing that, we notice that the entrainment ratio, which is, there it is. The entrainment ratio is a parameter that a lot of boundary layer dynamicists think about. It's the heat flux at the inversion height, the entrainment heat flux, divided by the surface heat flux. And traditionally, this has been, if you think about a boundary layer as being surface forced, it's this surface heat flux, which you can parameterize through some energy budget at the surface, and you get net radiation coming in that's driving that. And then that's what's driving the whole turbulent dynamics of a truly convective boundary layer. And that turbulence is actually transported up to the entrainment zone and driving this entrainment heating. So typically, people have used, just to make a closure so that they can quantify the entrainment heat flux, they use a 0.2, this kind of common coefficient people use. Well, we looked at that coefficient, and we noticed, these blue dots are from our data, we noticed that they're a very, very strong function of the wind in the boundary layer at that day. And if you look in the literature, there are a few other observational studies that found this as well. And I've tried to plot them here. The uncertainties, they'd only list like little tables with binned wind speeds, so these are not exact points, but they give you a sense of a similar sweep in this entrainment ratio that are driven by the wind speeds. So we think this is indicative that the wind at the top of the boundary layer in the valley strongly controls this entrainment. It's not simply a surface heat flux driven, which is what the classical boundary layer theory would indicate. So that's important. Now, we have a lot more faith in the daytime EPA flights because they're longer. They're 4 hours, they're over a smaller domain, so it's easier to kind of constrain everything and observe things thoroughly. But we still do the same analysis for the 15 other RLO flights, or residual layer flights of this project, in the different domain between Fresno and Bakersfield. And we get, again, a similar type of relationship with a lot more noise, which is what we expect. But this now is the entrainment velocity. Typically, this is non-dimensionalized by dividing by the convective velocity scale, which has that surface heat flux in it. So this is a way to sort of normalize out how much entrainment's happening because of the surface forcing. And we see that it has this strong relationship with what in the literature is usually proposed as an inverse Richardson number, and I've defined it here so you can see it. It's mostly driven by the mean wind speed at the top of the boundary layer. So this is an important finding, we think, that those winds aloft are really going to be what you need to forecast well, which we know WRF has a hard time with winds aloft. If we want to understand entrainment, we're going to need to know what the winds aloft are. So these are the 6 flights of the EPA, these thicker dots down here with a separate line. And you'll notice that the August flights, these are the August flights down here, seem to have a lower general entrainment than the July above. So we looked at specifically, well, what's happening meteorologically differently? And so this is a photograph from the airborne data from the first 3 EPA flights that happened at the end of July. And you can see that there's this stronger wind aloft in that buffer layer, that mid layer aloft that is going up valley. So it's oriented in the same direction as the boundary layer winds, but it's stronger. And if you look at the August flights, it tends to be a little more disorganized and weaker winds in general. So we feel like that's a sort of synoptic feature that is influencing the entrainment. So if you look at what's happening in the reanalysis data, just in terms of surface temperature, for example, if you wanted to forecast this, you see that in this case you have these surface temperature anomalies in the case of the stronger winds and therefore stronger entrainment in the southern Sierras. And this is the case of in August when the winds were much weaker and more disorganized. You can look at the pressure field or the geopotential heights in that level that's generated by the WRF, and you can see these are the flight patterns You can see that this thermal low, this heating at the surface in the Southern Sierras is driving this thermal low, and that's generally forcing a sort of northerly geostrophic component to add on to the thermal circulation of the valley mountain wind. And then in the cooler situation, you get actually a geostrophic forcing that's in the opposite, so you're weakening the background winds. So we feel like that's a important point to keep in mind if we want to track this entrainment, because that entrainment in the valley where the air's stuck, that entrainment is an important aspect of the air quality at the surface. Okay, so these are the data then, similar idea, budgets for NOx. We did the same thing for NOx. In NOx's case, we need to estimate the chemical loss term, and we do that with the Brune et al. Published OH values from CalNex. So we estimate OH and calculate what the loss of NOx is, and then back out everything from that budget term and solve for the emissions rate. And so the emissions rate we get is something on average after these 6 flights is about 190 tons per day. Now I've put here this the 65 as an uncertainty, and this is sort of, uncertainties are always, there's a little bit of subjectivity always with an uncertainty. So I've used the standard deviation of the errors of each individual error to estimate that. Now, we could argue about that, but the point is each measurement, we have a very, very, I guess you'd call it conservative, maybe it's liberal estimate of the estimated error. We try to put in everything we can think of and put it an error on the high side. And so we get these very large estimated errors for any individual flight. But we feel like if you go back 6 days in a row and you measure it over and over and again, that should narrow down that uncertainty. And so that's just philosophically why we present it as having this reduced uncertainty. But that paper that should be coming out in the next few weeks, Trousdale et al., we go through all of the arguments that indicate what could be wrong, interferences and so forth, and we present all those up front, and we still conclude that we think that it's higher than the ARB estimate, which is something like, for this area, is something like 100 tons per day for 2016. Similar we do for methane. We've done this before, published this in the past. Well, a different measurement, but similar results. We come up with the 375 tons per day in that region. This is a map of the CalGEM model estimate. So you can see that there are fairly large methane emission sources in that region. And if you just sum up the CalGEM estimate scaled to the 2016 total California methane emission estimate, then you realize we get a number that's about twice as big as what the CalGEM model predicts. So there's something going on there. This has also been backed up by this recent paper by Cui et al. From NOAA, who flew in the region, but they flew in a larger region than we did, and they got something like 700 tons per day, but that includes Kern and Madera, so it's an expanded region. But the important part is the ratio to the CalGEM inventory is similar. So they found it to be 1.7 from their study. So we feel like that's pretty solid result. So if we look at since we measured the ozone and the ozone production rate from the budget, so this is the budget now for ozone, and I'm showing you both the EPA flights in red. These are the averages for the 6 flights. And then all those 15 other flights were in the afternoon when we were flying down there. And that's the averages in the blue. So it's for a different domain, so they're not exactly comparable apples to apples, but you can still say, well, what was the measurement of NOx for each of those flights? And so when we plot the ozone production we get from this budgeting technique here versus NOx, we see a decent correlation. Again, the blue measurements we expect to have more scatter because they're not as focused and they're shorter. So this we feel like is good evidence that the ozone, at least when we go down there, which was typically targeting high ozone episodes, that it looks like the ozone production is NOx limited to a great extent. Okay, so we can start talking about the budgets. This is sort of framing this as a derivative. So because that budget equation is a time derivative, like many, many primitive equations are in physics and chemistry, that I focused on, okay, what is the time derivative of ozone as seen from the surface measurements? And so this thick line is the average of that network I showed you across the summer, that surface network, ARB surface network in that region between Fresno and Visalia. This thin line is the average for just the 6 days that we were flying, so it's a little bit different. And then these are the values. Remember, we fly for 4 hours or so, and we get average values for each of those terms in the budget equation. And this is what the color coding is, the average for that interval. So I wanted to match that to what we see on the ground and see how we can start tying this all together, the diurnal cycle. So this is the average photochemical production. We said was something like almost 7 ppb per hour for that extended 4-hour period. And then I've scaled this to JNO2 across the day, clear sky JNO2, just to estimate, just to give you a sense of what the photochemical production shape might look like. And then this is the average, the net growth, the net time rate of change, which matches the surface values fairly well on average, even though you're in this region that's plummeting here. And then these are the losses. This is dry deposition during the day. And this is a little bit of advection of cleaner air coming in, and also entrainment, that entrainment dilution I was talking about. Okay, so what this means then is if we start looking at these, carving it up in terms of these budget terms, then we see that, well, this peak that happens at about 7 or 8 a.m., this peak in the rise of ozone in the early morning, really has to be due to that residual layer entrainment, or that mixing that happens right in the beginning as you have that layer of high ozone from the day before that mixes down. And so we can start to see that this area, we can compare areas to this in terms of what the total production of ozone is. And we can see that it's comparable to the photochemical production, this downward mixing. Now, from our nocturnal data, which I won't get to today, we have averages between about midnight and 6 a.m. That look like this. So the chemical loss due to the production of nitrate, ozone and NO2, looks on average like this. And if you add dry deposition, which is weaker but still there at night, you get a total loss due to physical and chemical processes that looks like this overnight, which seems to add up to this average diurnal process. Okay, I'm going to skip that, and the rest is about the nocturnal jet, and I'm going to try to end because we're getting close to 3, and I don't want to over belabor this. But I just wanted to show you this figure because it's really quite stimulating. This is from the 15 now midnight flights and 15 sunrise flights we had. This is an average of the winds seen at 2 different layers. 0 to 300 is about where the nocturnal boundary layer is, the lower stable layer, and this is more like the residual layer. And so what we see is this really strong nocturnal jet. This is when the winds throughout the day reach their peak at about 11 or 12. That's why we targeted this flight at this time. And what you see is this up valley northwesterly flow, quite strong and active at night, both in the boundary layer and up here. The average height of the jet peak is somewhere around 300. So, and then if you look at the next day, you see that there's this sort of like inchoate, much weaker winds that happen, and some of them develop through the downslope flow throughout the region. So you do see some of this southerly flow. And this is what's generally characterized as the Fresno Eddy, right? But I just wanted to point out, in thinking about this and looking at the measurements over and over, we realized that it's not really an eddy that's constantly there that you can look at and put a balloon in and watch it kind of go around necessarily, because it's got these different distinct legs. The strongest leg is this northwesterly flow, peaks near midnight, and then this return flow is very weak and only occurs in the morning hours, and then it goes back to the up valley flow. So it's sort of out of phase. It's not a coherent eddy, but this is that idea of recirculation. And I wanted to just present that in the context of this buffer layer, meaning that there's this horizontal Fresno eddy that we think about, but there's also this vertical component where you have this up sidewall venting up the valley sides, which is also lofting and sort of recirculating on a diurnal type of time scale. So it's this recirculation really that focuses on it all. So I'm going to finish there? Oh, 15. No? Okay, well then I will keep going. How are you doing? Right, until you start throwing things or clearing your throat, I'll keep going. So Okay, so we've looked now at these, again, between the nighttime, the midnight flights and the morning flights, and we can kind of do this sort of macro budgeting between those two. And this is what potential temperature, ozone, this is NO, NO2, and wind speed. And again, I'm just layering these are averages, and this is sort of the average height of the nocturnal boundary layer is actually usually around 200 meters. The average was over 15 flights, and then the top of the residual layer, which is really where the mixed layer is about in the middle of the afternoon, is something like 600 or 700 meters. So you can see again at night, the ozone in the stable surface layer. You can see the stability here. The, not surface layer, I should call it the nocturnal boundary layer. The ozone is decreasing towards the surface, and the NOx builds up. The NO2 in particular builds up. And so the chemistry, I'm going to make this point, the chemistry between ozone and NO2, which is creating nitrate, which fundamentally, ultimately can lead to a loss of this, what we call OX, NO2 and ozone, therefore removing it from the system and not allowing it to remake ozone the next day. This loss rate is very comparable between these two because this reactant goes up, this reactant goes down, and so the reaction rates aren't a strong function of height. But the thing you have in the nocturnal boundary layer is surface dry deposition, and that's an important one. So this is how we do this budgeting between these two consecutive flights from midnight to morning. So this black line is what the average profile is of OX. So this is ozone plus NO2. This is what it looks like in the residual layer. You can see it looks very well mixed, and then you have this sharp gradient in the nocturnal boundary layer. And then this magenta line is what it looks like, that same average profile for the following morning when we fly. And so you can see there's this difference. And so again, we use this idea of a budget overnight to try to estimate the components that create this change overnight in the OX. And so what we do then is this blue line is advection. So we estimate from the horizontal gradients and the winds what the average advection is. That gives you this blue line. Then if you add in chemistry, which we know the principal reactants, ozone and NOx, we know what the reaction rate between them is, but we have to estimate what the ultimate fate of nitrate is. I'll get to that in a second. So, we make some estimates of that, and we see that's this green line when you add in chemistry. So the red line is when you add in chemistry and advection. This is what the morning profile and the nocturnal boundary layer should look like, this red line. But we see this magenta line. So we infer then the difference between the two has to be due to vertical mixing between the residual layer and the nocturnal boundary layer. And because we have the gradient, we can actually calculate what the eddy diffusivity is for overnight. So this is what that budget looks like, again, for each pair of flights. And then the average is down here, which is what I was focused on, kind of talking about the average situation, just to give you a sense of the fact that the chemical loss is about 2/3 of the total loss, and dry deposition is about 1/3. But these very much depend on what the fate of the nitrate is. Because nitrate can react with NO, if there is any NO around, and we do seem to see some NO around, very rapidly that just goes back to NO2. And so you don't get a loss of anything. You regenerate OX. But if you have the standard, textbook loss rate of this dinitrogen pentoxide, hydrolysis to, create nitric acid and all of that, that consumes 3 OX. So somewhere in between, and if you just do VOC reactions, you get 2 OX loss. So without knowing exactly what the chemical fate of nitrate is, we don't really have a good constraint on what the magnitude of this is. We kind of split the difference and shot in the middle with large uncertainty bars. But we're arguing that the ultimate fate of the nitrate radical overnight is really important to understand what the impact is on the ozone budget, the diurnal ozone budget. Okay, so, but back to this mixing. Even though this is only 1/3, this dry deposition may be 1/3 of the loss overnight, it still can be important. What we find is that if you look at the eddy diffusivity, sort of the intensity of this, the vigor of this mixing between the residual layer and the nocturnal boundary layer, and the following day's MDA8 ozone level, we see an anti-correlation, which is consistent with this idea that the more mixing of residual layer ozone down to the surface, where it can react with the actual surface, the more you deplete that reservoir, and it isn't there the next day to mix down and help produce the next day's ozone. So we looked at a 7-year climatology. We have the low-level jet from the radioacoustic sounding system, the sounder at Visalia, and the surface ozone at Visalia, and we compare the overnight low-level jet max observed at Visalia and the next day's peak in ozone, and we see an anti-correlation. Now, the R-squared isn't, of course, superb, but it is representing that, you know, has a significant role to play in determining the next day's ozone, how strong that jet is, because that jet is facilitating loss at the surface. And you can maybe even argue that beyond 12 or 13 meters per second, you never see a violation the next day. This is 1 hour ozone, so you got to be careful about those exact numbers. But we feel like this is an important aspect of forecasting ozone exceedances. And so we looked at the synoptic meteorology behind these jets. We found jets that went from a few meters per second on some nights up to 15 or 16. Well, you saw the spread here. In 7 years, you see it go from 3 or 4 meters per second to almost 25. And so we looked at that 7-year period and sorted them into regions where the jet was very strong on the left, and times when the jet was very weak on the right. And this is the 700 hectopascal geopotential heights to give you a sense of the synoptic meteorology around the situation. And so you can see that these pressure gradients are much stronger here, even though the flow is aloft, is across the valley axis. It still sets up this situation with strong pressure gradients that seem to be driving this strong nocturnal low-level jet. In this case of the weak jets, you see sort of the more pronounced trough, but it's much, much weaker. And in fact, the geostrophic forcing aloft is more like southerly flow. So we feel like this is something then that we need to keep our eye on in terms of forecasting ozone the following day because of this nighttime loss. Okay, so with that, I think I've covered everything that I wanted to. I feel like this data set has allowed us to really probe this 3-layer system. So you have a traditional boundary layer that's much more shallow than people, sort of the textbooks would indicate. And this was called out by Bianco et al. From NOAA 2011. Why are the boundary layers so shallow in the Central Valley? And we feel like this is because of this mesoscale circulation of the valley mountain flow. And what that does is that lofts this polluted layer from the surface that kind of gets stuck in this mid layer, this buffer layer, as the air flows in over the coast range and mixes with that, but stagnates. You have this sort of intermediate layer. And so this is a big, it's a conceptualization of how we think about stagnation and recirculation. It's happening in the vertical and the horizontal. We feel like this entrainment rate situation for any trace gas, or even the temperature budget. If you're interested in forecasting the temperature, we feel like this entrainment rate strongly depends on the wind speed aloft, and we know WRF has a hard time with the wind speeds as a function of height. And so we feel like working on that and improving forecasts of the winds aloft can help us improve this entrainment rate. This tends to be associated, just from what we've seen from that one summer, tends to be associated with the southeastern warm anomalies in the Sierras. That tends to drive a thermal low, which forces stronger winds in that mid layer, which enhances entrainment. We feel like this airplane methodology is very, very useful, and we can target small regions to get emissions or moderate regions to get emissions. And we feel like we can apply this at lots of different scales now. And the focus of this project was not NOx, so the emission rate of NOx may have been not as constrained as well as we'd hoped, but we can definitely concoct another project that could really, really focus on that. Because the modeling indicates that these soil sources of NOx are very, very site-specific. Okay, so, and then the last thing was this nocturnal jet. It was really fun to be able to fly at night all the way to the surface. which is very rare to do, and we were able to really probe the structure of this low-level jet, and we think that it has an impact on the ozone episodes due to its facilitating the surface loss of dry deposition overnight. So thanks so much for your attention, and I'd be more than happy to talk as long as you want about details of this. I think this is a shot from the cockpit again. That's probably too loud to take questions. So thanks. Any questions here? Yeah.
It's been a long time since I've had statistics.
Oh.
My ancient history says those R-squareds are not really very hot.
Oh yeah, there. This one.
Hi.
Right.
You mentioned at one time that R-squared didn't look very good, and I can't barely read it. Is it 0.168?
It's 0.17 for the 7-year climatology.
Yeah, and 0.46
For the 15.
Doesn't that mean that there's more error than there is correlation?
I think of it as you know, how much of the variability of the variable of interest can be explained by this one parameter that we're focusing on. So of course, if the chemistry, you know, if the loss of ozone overnight, that's only part of the equation, right? There's also this recirculation for residual layer, and the dry deposition loss is only 1/3 of the total loss overnight. So you're never going to get it's not going to explain everything, the jet, but I still think it explains something that's worthwhile and keeping an eye on. So the R-squareds, yeah, I agree. I mean, it's not like this, but you rarely have one variable that's completely determining another variable, right? In the wild, where you go out and capture data, and it's like, whoa. Especially turbulent data always has this great robustness of scatter. So I'm not, I don't see that it's worthless information. I just see that it's talking to one factor that's important, but only partially important, right? Important to this degree. Does that help?
So, yeah. Are those R-squareds typical for this kind of study?
Well, I've been, whenever I look at airborne, I've been working on turbulence for a while, and yeah, I mean, R-squareds are always they're never that good. I mean, I think if you're trained in the laboratory and you have a fixed concentration that's NIST traceable, you expect your instrument to track this one variable quite accurately. But in the real world and turbulence research, it tends to be much more scattered because you're not looking at completely determining variables. How I kind of see it.
So then the answer to your question is yes, these are typical.
Yes, they are. I would say, yeah. Is there anything online? There's no.
Just the audience. Someone's wondering about recordings, but.
Okay. All right. Well, thank you so much.